One of the big topics that we're going to be looking at in the atmosphere unit is the greenhouse effect. This is something that you probably have heard a little bit about in the media or maybe through school in the past. And there's a lot of information that is out there on this and how it connects to climate change, which we'll also be talking about. But wanted to start off with sort of some visuals to help you better understand. And this will be a starting point for our discussions in class. So we're going to start with kind of a question here to get you thinking a little bit about it and making some connections. Why is it dangerous to leave a dog in a car with the windows rolled up on a sunny day? So I'd like you to think about that a little bit. You probably all know that it is dangerous, but you may or may not know why. Add a comment to tell me what you think. You can use a text comment, you can draw, you can use your voice, whatever you want. If you want to draw a diagram as well, that's good. Explain your answer. We're going to use this model of the greenhouse effect to help us understand what is going on. You'll notice on the left side that this is the outer space. This is everything that is beyond the Earth's atmosphere. The sun would be out there and other planets and other things beyond our atmosphere. The atmosphere is in the middle, and then the Earth is on the right side. So if we were to start at the Earth and move outwards, we would go from right to left. I want to talk about these different molecules here. We're going to be using three different kinds of, well, two molecules and a photon, two different kinds of photons actually to help us explain things. Remember that molecules they are always moving around. When we have gases and liquids, they move around a lot. In solids, they don't move around very much, but they still do vibrate. Okay, there's some vibration that is occurring even in something like a rock. They're always moving. Now, there are different kinds of gases in the atmosphere. Remember, we've talked about this before. Carbon dioxide only comprises 0.04% of the atmosphere, but that's the molecule that we're going to be focusing on in this particular model. Okay. And on the left side, we have these visible light photons. These are tiny packets of energy that come from the sun. They are the photons that we can see. Okay. So when the sun's rays come towards us, we have visible light photons, those little packets of energy that are coming from the sun towards the Earth. Okay. Now, this model is somewhat accurate, but all models are inaccurate to some degree. We'll talk a little bit more about that in class, where the flaws are in this model, but there are a lot of things that can help you to understand as well. As always, if you have a question, add a comment. So as you can see in this slide, we have those visible light photons, those tiny packets of light energy coming from the sun, slowly traveling in a straight line to the Earth. So they actually enter and pass through the Earth's atmosphere on their way to the Earth's surface. So here you can see that visible light photon coming in to the Earth's atmosphere and continuing on until it reaches the Earth's surface. Now there is carbon dioxide and other greenhouse gases in the atmosphere, but those gases do not absorb the visible light. So visible light photons pass right past them, right past the atmosphere, and continues on until it approaches the Earth. When it gets to the Earth's surface, there are two different things that can happen. Either it can be reflected back into space, so head back the direction that it came from, or it can be absorbed by the Earth and then get radiated back into the atmosphere. So we're going to look at those two scenarios. So in this first scenario, the visible light photon is heading back out to outer space through the atmosphere. So just like it did on the way in, it's going to pass through. Just like it did on the way in, it's going to pass those carbon dioxide molecules and continue on its way. So the visible light can pass right by the carbon dioxide molecules and the atmosphere and continue on its way to outer space. This is the first scenario where it is being reflected. So here is the second scenario where we have a visible light photon that is coming, also coming from the sun, slowly traveling in a straight line to the Earth, passing through the Earth's atmosphere. And in this case, when we get to the Earth's surface, the visible light photon is getting absorbed by the Earth instead of being reflected. So in this case, we're saying that the visible light photon is being absorbed by a piece of rock, okay? A molecule that is part of a rock. And what's going to happen is that that photon is being absorbed by the rock molecule. Remember, the photons are little packets of energy. So when that molecule gets a little bit of extra energy, it's going to cause it to vibrate a bit more. Remember, they're always moving, always vibrating, but that little bit of energy is going to make it vibrate more than it was before. Now, you can't see those molecules moving in warm substances because they're really, really tiny. But if you were to touch that rock, you would feel that vibration in the form of warmth. So we all have experience with this. The sun's rays come in to the Earth's atmosphere. They warm things up on the Earth's surface. In this case, a piece of rock, okay, a molecule associated with the rock. So we can feel that warmth in the additional vibration. Now, eventually, after a while, that rock molecule is going to cool down or reduce its vibrations significantly. So, what happens at that point is that there is an infrared photon or heat that is being radiated by that rock molecule. So, for example, if a rock's been in the sunlight all day, we can put our hand a few inches away from it and feel the warmth coming off of it. So, we're actually feeling billions of infrared photons being given off by the rock molecules as the rate of vibration decreases. So, remember, uh, we had a visible light photon coming into the rock molecule to excite it, to make it vibrate more. As it vibrates less and starts to cool down, it radiates that heat energy, which is in the form of infrared photons. So while the visible light photons are things we can see, that's little packets of energy we can see. Infrared photons are little packets of energy that we can feel. You can think of them as little heat packets, okay? And what's going to happen is that that rock molecule is releasing the infrared photon, and they are moving away from the earth, being radiated away from the earth, and gets to the atmosphere again. Now, carbon dioxide molecule carbon dioxide molecules easily will absorb these kinds of photons. So unlike the visible light photons, which just pass right by, the infrared photons get absorbed by the carbon dioxide molecules. And that causes the carbon dioxide molecule to start vibrating, get excited. Okay, it's absorbing that heat energy. And so it starts to vibrate more. Eventually, the carbon dioxide molecule will cool down, just like the rock molecule did earlier, and it's going to release that infrared photon again. And what happens at that point is that there are a lot of options, actually. The infrared photon can head off in any direction at all. It can go back into outer space, it can go back towards the ground and get absorbed by another rock molecule, or it could go towards another carbon dioxide molecule, get absorbed again, excite that carbon dioxide molecule, make it vibrate, and then release it again. So remember, those little infrared photons, you can think of those as little packets of heat. Okay, that heat energy can go in lots of different directions. So the Earth would be uninhabitable if it wasn't for the greenhouse effect. And that effect is this piece, really, right here. Draw this. Where the photons coming in, the visible light photons coming in, are absorbed by that rock molecule. The infrared photons are released. Okay, that's fine. But the fact that there are carbon dioxide molecules that hold on to those infrared photons, release them, and some of them go back to the Earth's surface. That is the part that is very important for our survival. Um, there, that makes greenhouse gases like carbon dioxide very important to us. If we did not have that small amount of carbon dioxide and other greenhouse gases in the atmosphere, it would be an ice age on Earth. Um, it helps to maintain, they help, those gases help to maintain the Earth's temperature at a comfortable level. And we've always depended on having that greenhouse effect, having that cycle where this infrared photons are absorbed by the carbon dioxide molecules, released, and some of them coming or reflected back to the Earth's surface. That is really important for our survival. However, what we are seeing is that there are more carbon dioxide molecules and other greenhouse gases in the atmosphere than what we have had for years and years and years. So I want you to add a comment here and tell me, what do you think will happen if we add too much carbon dioxide into the atmosphere? We know that the visible light photons are able to pass through to get to the Earth's surface. But what about those infrared photons? What's going to happen to them if we add more carbon dioxide into the atmosphere? You may have heard the term greenhouse gases before. In this model, we have been using carbon dioxide, which is CO2. But there are other common greenhouse gases that act the same way as carbon dioxide does. Some of the more common ones are methane, CH4, water vapor, H2O, and nitrous oxide, N2O. These gases are alike in that they all have chemical bond configurations that allow them to absorb those infrared photons. So remember, just like we saw in the model for carbon dioxide, all of these gases will absorb that infrared photon as it is being reflected back up into the atmosphere, vibrate, and then release it. And when they release it, it can go into outer space, back towards the Earth's surface, or laterally into the atmosphere where it can be picked up by another greenhouse gas. So they all are alike in that way, even though we're using only one of them in this model. These are the most common ones, and all of them are have the same sort of impact as what carbon dioxide does. Now, there are things that are happening on Earth that are intensifying the greenhouse effect, increasing the amount of carbon dioxide and other greenhouse gases that are in the atmosphere. One of the biggest factors is burning of oil, natural gas, and coal. That burning combustion reactions, those have a huge impact on the carbon dioxide emissions. And another factor is the fact that we don't have as many trees and plants as we used to, that they cannot absorb that carbon dioxide. Remember that cycle that we were looking at with photosynthesis? Those plants take in that carbon dioxide and produce oxygen. They cannot keep up with the amount of carbon dioxide that we have in the atmosphere. And so they are not able to do enough photosynthesis in order to absorb all that carbon dioxide. Take a look at this graph, this pie chart that shows around the world which sectors are responsible for generating different percentages of all the greenhouse gases that are produced in the world. Take a moment, look at it. Is there anything in here that surprises you? Add a comment. So now that you have a better understanding of the greenhouse effect, I'd like you to add a comment. What are some things that you could do to make it safer for a dog to stay in a car on a sunny day? So once again, add a comment, looping back to that question that we asked at the beginning about why it's not safe. What are some things that you could do? Think about what you've learned in the greenhouse effect here to help you with your answer.